Hi guys, welcome back to another video. We're revisiting ionization energy because this is the part I skipped because we didn't know orbitals. But now we know orbitals, we can do this. And what we're doing is we're looking at why. Well, let's go back to here. We saw that it increases as we go along the period of the periodic table. So as we go along a row, so like from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine, it increases the ionization energy with some exceptions. And we're going to look at those exceptions now. So these exceptions are here. I've circled them with giant red circles. And as you can see, these buck the trend. So you'd think that boron had a higher ionization energy compared to beryllium, and oxygen had a higher ionization energy compared to nitrogen, but they don't. And by looking at their orbitals, we can find out why. So let's have a look at this. Beryllium, it's element number 4 and boron is element number 5. So I can go to my trusty paint. I know that boron has got 4 electrons, and I can pencil this in. And I can draw my 4 electrons onto boron. 1, 2, 3, 4. That's nice and stable. It's got 4 electrons. Both of its 2s shells are completely filled. When we go to, no, that's beryllium. When we go to boron with 5 electrons, we have to put it there. This electron is in a much higher energy orbital. It's in the 2p orbital. It's all by itself. Hence, it's easier to remove compared to this stable configuration of beryllium. Hence, beryllium, with the 4 electrons here, has a nice stable configuration. It's lower in energy, meaning it's hard to remove 1 electron. It's harder to remove this 1 electron from beryllium as it is to remove this higher energy electron that is in boron. So the meaning, when we go back to here, we can see that it takes less energy. This is ionization energy here. It takes less energy to remove this high energy electron from boron than it is to remove the stable electron from beryllium. Let's go up to nitrogen. Nitrogen's element number 7, so we can just add a couple more things to this. 1, 2, 3, 4, 5, 6, 7. So that's nitrogen. Nitrogen has singly occupied all of its 2p orbitals, and that's when it has them all filled, singly occupied. That's nice and stable. It minimizes repulsion, and so it minimizes energy, maximizes the repulsion of the electrons, so it minimizes the energy of the system. So it doesn't want to lose this 1 electron because it's nice and stable like this. When we go to oxygen, we have to double up on our electron. So that is suddenly not as stable. Hence, this electron is easier to remove, and it takes less energy to remove this electron of oxygen. Because remember, with ionization energy, we're just removing 1 electron. So with nitrogen, we've got all our p orbitals with 1 electron in them. Oxygen, we've added 1 electron to our p orbitals, which has got a pair, meaning it's now easier to remove, and hence it's lower in energy. The same thing happens over here with magnesium and aluminium. With magnesium, we've got this. So that's 10 electrons. This is 12 electrons. So this is magnesium. Oh, sorry. This is magnesium with 12 electrons. Aluminium has got 13 electrons, and this is happening. There is 1 electron in its 3p shell, meaning it's easier to remove. So aluminium has got a lower ionization energy, as we can see here. Aluminium's got a lower energy compared to magnesium in terms of how much energy it takes to remove 1 electron from it. Okay. Next one, phosphorus and sulfur. Same thing happens here. This is phosphorus, which is nice and stable because they're all singly occupied. When we double them up here, this is suddenly easier to remove to get back to this stable configuration. So let's look at the notes for that. In groups 2 and 13 elements, there's a small decrease in ionization energy along with 15 and 16. So by group 2, I mean between this and this. Since this is group 2 and this will be group 13 or group 3, depending on if you count the transition metals in between. So this is between group 2 and 3, this is between group 5 and 6. There's a small decrease. Between here, this is 5 and 6. These are some notes for your book to put in. As an element moves from having electrons in an s orbital to a p subshell, or s subshell to a p subshell, for example beryllium to boron and magnesium to aluminium, the ionization energy decreases. Electrons in the p subshell have a higher energy than those in the s subshell and are easier to remove. Cool. As an element moves from having unpaired electrons to paired electrons in their p subshell, so I'm going from nitrogen to oxygen and phosphorus to sulfur, the ionization energy decreases. There is extra electron-electron repulsion from the paired electrons, making the paired electrons easier to remove. The new paired electron is easier to remove and hence has a lower ionization energy. Fantastic. So there'll be a small task in the Google Classroom to help explain this, and yeah, get these notes down and have a great day. Thanks for watching.